Welcome to lesson 23. Today we're going to be looking at the properties of logs. In the last lesson you got to find out what a log was, and it is an exponent, right? A log is an exponent. You keep that in mind. And then today we start finding out some of the good properties of logarithms, which is why Mr. Napier thought that they'd be so helpful to us in calculations. And those properties help us tremendously with some simplifications and solutions today. Okay, so let's get started. First off, just a quick review. And I didn't really ask this question in the last one, but let's see if this makes any sense. Between what two integers, consecutive integers, will log base 3 of 30 fall? I'd like for you to think about that for a second. Log base 3 of 30. Log base 3 of 30. 3 raised to what power will give you an answer of 30? Well, I think you realize 30 is not a power of 3. But if you play with it for a minute, you realize 3 to the third is 27. 3 to the fourth is 81. So log base 3 of 30 should be a little bit more than 3. Right? That's some good thinking, and it shows that you really understand what's going on if you can understand that log base 3 of 30 is going to fall between 3 and 4 and actually be closer to 3. Well, in the last one we played with these crazy things. E raised to the natural log of z plus 9. Now what's the base on that, ln? He is base E. So this is effectively asking the question, this exponent, E raised to what exponent will give you an answer of z plus 9? Well, whatever that happens to be, if I raise E to that exponent, I get z plus 9. Okay? Now, we want to do a little bit of playing along here. Wow, there's a lot of stuff up here for us to look at. I just want you to get comfortable with why the properties are what they are, that this isn't just some kind of magical thing that happens. On the left-hand side, we have log base 2 of 4 times 8. Now, your algebra training tells you that would be log base 2 of 32. 4 times 8 is 32. 2 raised to what power gives you 32? That would be 5, right? 2 to the 5th is 32. Okay, well on this side, you'll notice that you have addition. That would have to come last. So what is log base 2 of 4? 2 raised to what exponent gives you a 4? That would be a 2. 2 raised to what exponent gives you an 8? And 2 plus 3 is 5. So interestingly, I came up with the very same answer for this log base 2 of 4 times 8. And over here where I found each of them separately and then added them. Okay, mildly interesting. Okay, log base 3 of 27 times 1/9. Order of operations tells you do what is inside the parentheses first. So that's what? Log of 3. And then 3 raised to what power gives you 3? And that would be a 1. Okay, then over here. Log base 3 of 27. Do you know why that's a 3? 3 cubed is 27. Plus 3 raised to what power gives me 1 over 9? That's a negative 2. And when I add, I get 1. Okay, so again, it's kind of interesting. It's a little bit more interesting that it happened again. And so then the mathematician says, well, you know, instead of continuing to play with numbers, what if I start looking at a general case? What if I look at log of any generic base of b to the m times b to the n? Order of operations says that we must do this multiplication first. And when we multiply, what do we do with the exponents? As long as these have the same bases, we add those, right? And then the question is, b raised to what power gives you b to the m plus n? That is m plus n. Okay. And then over here, log base b of b to the m is m. Log base b of b to the n is n. And right there is what makes it extremely interesting, that I know in the general case that these two quantities have to be equal to each other. Hey, you know what the big crux of this was? And it's something that I keep saying and saying and saying. Logs are exponents. And look at what happened here. Because of the multiplication with the exponents, we added those exponents. And over here, the logs are exponents. They were added. It's because multiplication with like bases, you add your exponents. Okay, it kind of makes sense with it all. Okay, let's try this next guy. We have log of 10,000 over 100. Now you know that's base 10. And I believe that that's going to be 100 when we divide, because order of operations says I should divide first. And that gives us a 2. Log of 10,000 is 4. Minus log of 100 is 2. And we get 2. So now the situation's a little different. I'm not multiplying inside, I'm dividing. And when I divided, I got the same answer as if I took log of each of them and subtracted. That's kind of making everything roll here. Now, if I reduce this fraction, you may not realize that 625 happens to be 25 squared, but it is. So 5 raised to what power gives you 1 over 25? Negative 2. Log base 5 of 25 is 2. And since this guy is 25 squared, that's the same as 5 to the 4th. And we, again, get that negative 2. Okay. And that's all well and good, but it's awfully nice if I can then look at the generic case, the general case, and I see, okay, I've got division. Now, when I'm dividing and I have like bases, what do I do with the exponents? I subtract them. B to the m minus n, and then log base b of that is m minus n. And on the right-hand side here, when I do them individually, log base b of b to the m is m. Log base b of b to the n is n. So I got the very same answer both ways, which means that this quantity has to equal this quantity. In essence, we just derived or proved, whichever way you like to think of it, a property of logarithms. Like we did with the multiplication, now we've done it for division. And there's 1 to go. Log base 2 of 2 to the 5th. Well, let's see here. What's 2 to the 5th? We had it up there. 2 to the 5th is 32. And let's see here. 2 raised to the 5th. Now here we get 5 times what is log base 2 of 2? 1. And we get 5. Natural log of e to the 7th, well, that's just 7. You know, we did some of these before. This is saying e raised to what power is e to the 7th? 7. Here, 7 times the natural log of e to the 1st is 1, and I get 7. And in this case, it's saying log base b of b to the m. To what power do you raise b to get this? Well, you're looking at it, it's m. And over here, I have m times log base b of b, which is 1, and I get m. And on this last guy, by the way, what you've got going on is essentially that you're raising a power to a power. And when that happens, you multiply the exponents. And one of those exponents was the m, and one of those exponents was the logarithm. Okay? So, as it turns out, there are 3 very important basic log properties. If you have a product, you can actually split that product up into the sum of 2 logarithms. And it makes sense because if you're multiplying and you have like bases, you add the exponents. Now, by the way, we're going to actually work with these properties in both directions. It also means that if I have the addition of 2 logs and I have the same basis, I can condense them into this statement. Remember my stupid little story about the ants going out on vacation? An equation works either direction. So I can take a logarithm and expand it, or I can take logarithms and condense them using these properties. In the case of division, if you're dividing and you have like bases, what do you do with the exponents? You subtract them. And what are logarithms? Logarithms are exponents. And the last one of the properties, and this is the one everybody loves, make sure you're always in logarithms when you're using this. You get to bring that exponent down in the front. Okay? Now you do have to make sure that that exponent is applying to the entire argument in there, by the way. So if you have essentially a power to a power, you multiply your exponents. Now remember, you can go both ways, so that coefficient sometimes goes up as an exponent. Take a second and read my statement. You know what goes in those spaces? Well, if you've been listening, you know, because I've said it a gajillion times, exponents, 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 exponents. Logarithms are exponents. Okay, so we want to use those properties to expand, and then you just love a statement like this. Simplify as much as possible. Okay, well, with some experience, you'll get the hang of how we do this simplifying. I see multiplication, so I can separate that into addition of 2 logs. Yeah, that was our very first property. Now you might say, why would you do that? Well, log base 10, remember that's a base 10, log base 10 of 10 happens to be 1, right? So that's that simplify idea. That becomes 1 plus log of 2. Now, you're going to leave it here at this point in time. But back in those old dark ages when I was a student and we used logs for calculations, I would have to use this property, and I can still remember from way back in high school that the log of 2 is about 0.3010. So I would then immediately say the log of 20 is about 1.3010. And if you want, you grab a calculator and you ask it, what's the log of 20? That's what it's going to tell you, okay? And it is really cool because with that very same idea, I can find the log of 200 and the log of 2,000 and the log of 20,000. And it's all using the properties of logs. Okay, with this guy, we're in base 2, so we're not in Mr. Briggs's common logs. And we have division, that's the big operation going in there. So that says subtract your exponents minus log base 2 of 9. Now we did apply the property. If you have division, it becomes subtraction of the exponents. Then you take just a second and say, well, can I simplify either one of these? 2 raised to what power gives me 16? I can do that guy. That would be a 4. Now, 2 raised to what power is 9? Not anything pretty. And if it's not pretty, then it's going to be one of these irrational numbers where the decimal just continues on forever and there's no repetition. So our exact answer is log base 2 of 9. Okay? And at least we know something about it. Log base 3 of x to the 4th over 27. And when I see this, and my directions are still to expand it, I see a big division. So I say, oh, division, that means I subtract my exponents. So this is going to be log base 3 of x to the 4th minus log base 3 of 27. Hey, you might have said, why didn't she bring that exponent out in the very beginning? The reason I didn't is that that exponent is only applied to the x that's sitting up in that numerator. If it had been x over 27 raised to the 4th, all of it, then I could have brought that out. But since it was not applying to the 27, it was wrong if I would bring that out, okay? But now that I have this subtraction, I do have that exponent applying to the entire argument, so I can bring that 4 down in front and say, well, it's going to be 4 times log base 3 of x. And then I look at this and I say, oh, I can simplify that because 3 cubed is 27, so that is a 3. And you know, believe it or not, that may be really helpful if you're doing some science problem or whatever, working with logarithms. It may help you solve this and be able to more easily find out what x is. Okay. And again, we're expanding, and I see a big division going on here. So we'll have log base 5 of 125 minus log base 5 of the denominator. Okay. And depending on your comfort level, you might be able to look at that first term and know right away, oh, 5 cubed is 125. This is equal to 3. Hey, a suggestion that I've given in class just recently, as we've been working with these logarithms, is if you're not comfortable with these powers, you might want to have a table that you've written out on paper. Write down some powers, meaning this. 2 to the first is 2, 2 squared. And in fact, if you want, you could even go up and do some of the negatives as well. Just to make yourself think about those, 2 squared is 4, 2 cubed is 8. And I know these little ones you're more likely to just see right away, but maybe not. And especially when you start seeing 32s and 64s and so forth. And then you might want to write out some powers of 3. One of my favorites, for some reason, 243. Anyhow, you might want to make several of these, and then when you start seeing these numbers, instead of sitting there trying to start from scratch every time, you might just look to see, hey, is that one of my powers? And of course, if you're working in base 5, these aren't going to help you any. You would want to look down through the powers of 5 and see if you find a 125 in there. Okay, just a suggestion. Now, as it turns out on that second term, this guy right here, you might look at that and think, well, I can't do anything except a square root is a power. You know, it turns out that, if you guys go back and think about fractions and decimals, like if I have 7 over 5, he happens to be equal to 1 2/5, if you like, which is the same as 1.4. And there's situations where 7/5 is a nicer way for us to think about it. And there's times when 1.4 is a nicer way for us to think about it. And the same thing is true when it comes to fractional powers. Like if I see the square root of 9 and I see 9 to the 1/2, this one feels more comfortable for me that I say right away, oh, that's 3. This one, I have to think, oh, that's the square root of 9. Yeah, that's 3. Okay? But as it turns out, sometimes dealing with the square root of x is just not as comfortable for me as dealing with x to the 1/2 power. For example, if I have to raise it to, say, the 6th power, I have to do some thinking here with roots, whereas with the fractional exponent, I can just say, oh, 1/2 times 6, that's the 3rd power. My point being, you just have to get used to the idea that sometimes we like seeing the radical and sometimes we prefer having the fractional exponent, and you just need to be able to adjust in the situation. Okay? Well, in this situation, you want to realize that that's a fractional exponent. It's moving slowly. And that would be, if you like, we'll write it out again, x minus 3, all of that to the 1/2 power. And since that 1/2 is applied to the entire argument, I can bring it down in front, and I have 3 minus 1/2 log base 5 of x minus 3. Do not think you distribute through. LOG here is the name of a function, okay? It's kind of like the outside of that pop machine. Remember that silly pop machine from way back in like lesson 2 or 3? Yeah, you can't touch that x minus 3 because that's inside of the function, okay? Well, this is a lovely mess. I'm supposed to expand it, and I see that the overriding operation in there is big fraction bar. And then I have crap on the top and crap on the bottom. So I start by dealing with that, and I say it's going to be natural log of numerator minus natural log of denominator. Then, like so often in algebra, you have to kind of look at it to see, well, am I done or should I continue? Well, I see that I have a multiplication in there, so this would be natural log of z plus natural log of the square root of x. Remember, multiplication gets split up into addition because we add exponents, minus natural log of y to the 4th. Yes, I hear the clamoring. Bring down the 4, bring down the 4. I could have brought down the 4 on that step if I wanted to, but I'm also thinking this guy is x to the 1/2. So I've got natural log of z plus 1/2 natural log of x minus 4 natural log of y. And I would leave it right here. That is expanded as much as I can and simplified as much as I can. And I know you look at that and say, that is just gross. But it may allow me now to do some combining of like terms. I might actually be able to get somewhere because I can deal with those properties. Okay? Hey, do you notice that in this case, that index of 5 on the root, that's overpowering everything. So this is saying log base 3 of x squared over y, all of it raised to the 1/5. Because of that, now you really have two options here. Because of this, I can bring that 1/5 down at the very beginning. Now the other option, and some of you might say you like it better, and that's fine. You can actually apply that exponent to the numerator and to the denominator because we have a variety of properties in exponents. For example, if I have a product raised to a power, I can apply that power to both of them. I am not distributing it through. It's a matter of you have n of these multiplying, you're rearranging the terms. If I have a over b raised to the nth power, think about how I multiply fractions. This is a over b times a over b times a over b times a over b. I multiply all the way across the top. I multiply all the way across the bottom. Now these are two useful properties out of exponents, and it's not that I'm distributing. It's that I understand how to multiply fractions, and I understand the commutative property and associative properties. Okay, I'm going to bring that 1/5 down, and I'm going to say that's 1/5 times log base 3 of x squared over y. Next step, you see that I've got a big division going in here, which means subtract. Now, I don't want to forget that this 1/5 is being multiplied times everything. So I'm going to put parentheses, and it's log base 3 of x squared minus log base 3 of y. The last thing to do is to bring that 2 down, and I would leave it like this. I would say 1/5 times 2 log base 3 of x minus log base 3 of y. Now, granted, if I distribute the 1/5 through, I can get rid of the parentheses, and you might like it better that way. That's fine. Okay? But I do have it all expanded, and because these are base 3 and I have x's and y's, I'm done on the simplifying front. Okay? Wow, we keep getting these guys, don't we? Bring that 4 down in the front. Now, why am I allowed to do that right away here when I wasn't in some other situations? Because that 4 is applied to the entire argument. And now I'm done. Well, now these have already been expanded, and we're going to try to condense them. Okay? Because both of those skills can be useful to you. So we're going to kind of go backwards of what we did before. For example, do you realize that multiplication, in essence, trumps addition? It's done first. I'm going to run this power up because this 3 is only going to get applied to this argument. So I get log of x cubed plus, run that 4 up, log of y to the 4th. Hey, what's my base? I'm base 10. So we applied those exponents up, and now we see that we have addition. When do we add two exponents? Well, we add two exponents when we were multiplying the inputs. So that becomes x cubed times y to the 4th inside of that log. Okay? Now on this second one, the 1/2 goes up as an exponent because he's only applying to that x. And the 1/2 power is the same as square root. So this is ln of the square root of x minus ln of z. And you know, you don't have to always use those parentheses. Lots of textbooks don't use them very often. I probably use them a little more than some authors do. I just like to sometimes use them to make absolutely sure you know I'm talking about function input. Now, if I'm subtracting exponents, what had to be happening? Division. So that becomes natural log of square root of x divided by z. And I'm done. I have it all into one log statement. And sometimes that's a very handy thing to be able to do, depending on the problem you're working with. Okay, I've got a log plus 2 times log base 5 minus 3 times log base 5. Everything is base 5. That's good, because if they're not the same bases, you cannot condense them. Well, without doing something else first. And I'm a little bit concerned about this minus only because I've got a more complicated situation here. So what you might want to do is think back to pre-algebra days. Remember all the way back to pre-algebra? When your teacher always did plus negatives. Now, I'm not a huge fan of plus negatives, but there was a reason your pre-algebra teacher had you do that. If you're ever in a tight situation, it just helps you make sure you're very careful. Because essentially, that means that that coefficient is a -3 as I take it up as an exponent, okay? Now, I think you realize that addition gives me multiplying, and so I'm going to be multiplying by the reciprocal, which is the same as dividing. Are you with me on all this stuff? Okay, I'm going to take those exponents up, and I get log base 5 of x plus log base 5 of y squared plus log base 5 of 1 over x cubed. Now, why did that end up down in the denominator? Because of that negative exponent. And now it's all multiply, because this is all addition and I'm adding exponents, so the multiplication is what was going on, and I get log base 5 of x times y squared over x cubed. Now you might look at that and say, can you cancel an x? Yes, I can. I can make that log base 5 of y squared over x squared. All right? And there are some other ways to leave that. Now, by the way, you might have been hollering earlier and saying, hey lady, notice that I actually had like terms in the very beginning. Now, I purposefully went ahead, just proceeded as if I didn't see them. If you saw those like terms, then here's what could have happened in that problem. And in all honesty, it's a good idea to see that, but if you don't, it's still going to work out. I have my 2 log base 5 of y, and then if I combine these two together, I would have minus 2 log base 5 of x. And then, if you want to be really snazzy about all this, you could say, hey, factor that 2 out. And I have 2 times log base 5 of y minus log base 5 of x. Subtraction of 2 exponents means you must have been dividing. So it's log base 5 of y over x, and then run the exponent up, and we get log base 5 of y over x quantity squared, which, written differently, but saying the very same thing as what I have in that other way. 2 very good approaches, and there's even more, okay? Number 4. Again, because I see 4 of these, and I think you would have handled the subtraction okay up there, even if I hadn't changed it into a plus negative. But when you get 2 of them, 2 or more, that's when students really start to get uncomfortable. So let's change this to plus negative 1 and plus negative 1 times. And the reason I'm doing that is so that I take up both of those as exponents. So this is going to become natural log of x plus, hey, you know, if nothing else, you should like ln's because it's less writing. And it gives me plus natural log of 1 over 15 plus natural log of 1 over x plus 2. And the nice thing is that as long as all you see there is addition, I'm adding all these exponents, it means all of the inputs were multiplied. So I can do one humongous happy multiplication here, and I get x times x squared minus 4 over 15 times x plus 2. And as long as x is not negative 2, which it would make no sense, because remember the domains of all of my logarithms are positives only, I can actually cancel out a like factor here, because x squared minus 4, you know, is x minus 2, x plus 2. So I can cancel out the like factor and actually simplify this one more step and say natural log of x times x minus 2 all over 15. Now some of you might say, oh, you should have multiplied that x through. If you would like to, go for it. I probably would leave it unmultiplied, because I find that a lot of times they're very handy to leave things in a factored form when you're not sure what your next step might be in a problem. Okay? Well, now we're going to get to do a little bit more practicing as far as how these guys were really handy numerically. And again, it's just applying properties. With that information, I want to know what is log of 200. Let's see here. Well, that is, and all I know is log of 2 and log of 5. And this is base 10, so I can use any 10s I want. So this is 2 times 100. We saw a problem like this at the very beginning. So using my property, if I'm multiplying on the input, I get to add my exponents. And my logs are my exponents. Log of 2 is approximately 0.3010, and log of 100 is 2, so I get that this is approximately equal to 2.3010. And what's really nice is if we're dealing with LOGs, base 10, you've got buttons on your calculator for base 10 and base E. Now, unless you've got a special calculator, you don't usually have those other bases, all right? Now, in this case, what am I going to do with a 0.2? Well, you might realize that, okay, that's a decimal, and decimal is a word that's short for decimal fraction. That's 2/10. And I could work with that. But somebody else says, wait a minute. Isn't 2/10 the same as 1/5? Yes, it is. Which that would be the same as the log of 5 to the negative 1 power. Because see, I told you what log of 5 was. So that would be negative log 5. And so it's approximately negative 0.6990. Grab your calculator and check that puppy out. That's what you should be seeing. Now, by the way, if right here you separated that into subtraction, you go right ahead and you should get to the very same answer. Okay? Number 3, log of 4 over 5. Well, I know that is subtraction. So we have log of 4 minus log of 5. And I have a decimal for that guy. I don't have a decimal for log of 4. But 4 is 2 squared, right? So this is log of 2 squared minus log of 5. So I've got 2 times log of 2 minus log of 5. This is how we had to do some of our computations at times. Well, let's see here. 2 times that guy would be 0.6020. Subtract 0.6990. This is an approximation now. And I believe you're going to come up with a negative 0.097. Okay, if I subtracted right. Okay? Now, how about the log of the square root of 50? Well, hey, we can deal with that square root, right? Because the square root is the 1/2 power. So we just have to figure out how we deal with the 50. Okay, so let's see here. This would be the log of something to the 1/2 power. Now, how can we break down 50? Well, we could just say 5 times 10, couldn't we? That's one option. The other option is I could make this 5 squared times 2, but I don't necessarily want to deal with both of those decimals. So I think this may be easier for me. So this is going to be 1/2 times log of 5 plus log of 10, right? Multiplication gets split into addition. Well, let's see here. 1/2 of the log of 10 is 1. Add it to that guy. So I have, this is an approximation, 1.6990. And that should be about equal to 0.8495 maybe. Yeah, you can double check that. And what's really nice is you can ask your calculator, what's the log of the square root of 50? And I'm guessing that's real daggum good. Okay? Recap. Let's recap these properties of logs. And you do need to be comfortable with the properties of logs as we start applying them to solving equations and so forth. Logs are exponents. Did you get that? Logs are exponents. And since they're exponents, the properties of logs are going to be related to the properties of exponents. You don't have to learn these properties of logs as if there's something totally new and foreign to you. It is simply looking at the properties of exponents in a slightly different way. And please apply these properties using your order of operations. That makes it all work out really nicely. And practice, practice, practice on these guys. And I'll see you in the next lesson.